So as I mentioned, we start out with some relatively basic math concepts because that's where the problems usually start for people in math. In fact, I'm going to start out with probably the simplest math concept, but also the one that is most misunderstood, and that is, what is a number? For most of you, show of hands, if I put a 4 up there, how many of you would say that's a number? Most people would, but it's not complete. That's what we call a numeral. It is just an amount. To truly be a number, it has to tell us not only how much, but of what. So like 4 cows, that's a number. It tells us how many, in this case 4, which I'm going to call the count. And it tells us of what, in this case the cows, which I'm going to call the name. Now you might be sitting there thinking, oh no, another one of those teachers that's going to make us label everything that's going to be marked wrong. And normally I'm not like that. But in this class, since you guys are all in the medical field, it is very important. If your answer is 12, is it 12 microliters or milliliters? That's a big difference. 12 grams or 12 milliliters, and so on. So for us, there is going to be a little bit more weight put on including those labels. But for right now, the purpose of it is to show how the numbers really interact with each other. To show the importance of those two parts of the numbers, let's take a look at our most basic math operation. Addition and multiplication. Now you might be thinking, where'd subtraction go? I thought that was the second most basic operation. Well, subtraction really isn't its own operation. Subtraction is really part of addition. It's just going in reverse. So anything that we discuss for addition also applies to subtraction. And the same for division. Division is just kind of a byproduct of multiplication. It's multiplication done in reverse. So anything that applies to multiplication also applies to division. So let's do an example here. Let's say we take 4 inches plus 7 inches. What do we get? 11 inches. Good. Probably not, what you were looking for out of today, but let's break it down into the two parts of the number. For the counts, we had 4 and 7, and it became 11. We combined the counts. We're adding, so we combined them with addition. But if we look at the names, we had inches, and it stayed inches. When we add numbers, we keep the same name. Now again, you're probably sitting there thinking, oh, big deal. But when we multiply, there's some key differences. When we multiply, let's do 4 inches times 7 inches. First of all, is there anybody out there that's not familiar with the dot for multiplication? It means the same thing as the little x. We don't get it confused with variables later on. So 4 inches times 7 inches will give us 28, but it's not inches, it'll be inches squared, or square inches. When we multiply numbers, if we look at the counts, 4 and 7 became 28. So we still combine the counts. The difference comes in the names. Here we had inches, and it became square inches, or inches squared. When we multiply, we also combine the names. Now you might be looking at that thinking, okay, that's something I didn't know, but I still don't see why it's so important. This is actually the single most important concept in math because it explains why we do everything we do with all the different forms of numbers. First of all, it actually even tells us what we can and can't use in each operation. For example, back to the 4 cows. Let's say I have 4 cows plus 3 boys. Does that give me 7 cowboys? It doesn't work that way, does it? Or if I did it the other way around, 4 boys plus 3 cows, is that 7 boy cows? No, it's not. Anybody with a farming background in here? Yeah, a little bit. You can tell me that this is a whole bunch of both. Oh, a long way to go for a joke. But there's a point behind it. We cannot add 4 cows to 3 boys because they don't have the same name. Because when we add numbers, we're going to keep the same name, which implies that we have to start with the same name. We can add inches to inches. We can have cows to cows and boys to boys, but not cows to boys. They must start with the same name. We might even have like 5 feet plus 2 pounds. What do we get when we add those? Well, trick question. We get 5 feet and 2 pounds. They have different names. They cannot be combined with addition or subtraction. When we multiply, however, we also combine the names, which means that 5 feet and 2 pounds can be combined with multiplication. We're going to combine the counts. 5 times 2 makes 10. Then we're also going to combine the names. Feet times pounds are foot-pounds, which is a unit of torque. So when we multiply, we don't need the same name. Now again, you're probably still looking at that thinking, okay, big deal. And with whole numbers, it's always been pretty obvious. We've always done it. It doesn't make a difference to us. But when we understand that about whole numbers, the stuff we do with our other forms of numbers makes more sense. For example, fractions. Everybody's favorite type of number, right? If I were to ask people on their way in the door what they hate most about math, 4 out of 5 people would probably say fractions. You're there? The other 1 out of 5 would usually say the teacher. Just a little review. What's the top number? The numerator. The bottom number? Denominator. You saw me pause there a little bit. I am a horrible speller. I a lot of times get halfway through a word and have to stop and remember how to spell it. I also admit I have kind of poor handwriting sometimes. If there's anything ever appears up on the board that you don't recognize, I assure you it was intended to be English. I probably either butchered the spelling or my handwriting's horrible or both. Don't be afraid to jump in and ask me what something says. I'll never be offended by it. So anyway, the numerator. What does it mean to numerate? Well, every 10 years, our government sends out people to do the census to numerate the population. What are they doing? They're counting. To numerate means to count. Denominator. Well, we have different denominations of bills, of money, different denominations of organizations. To denominate means to classify or to give a name. So when you look at a fraction, a lot of people see 2 numbers, a 3 and a 7, but it's not true. It's a single number with 2 parts, a count and a name. So when we go to work with those fractions, 3/7 plus 2/7, somewhere back around 3rd grade or so, you had a teacher that told you that when you add fractions, you must have a common denominator. That is not a special rule for fractions. When we add any numbers, we must have the same name. And when you add those fractions, you're going to combine the numerators. 3 plus 2 makes 5. And you're going to keep the common denominator. Again, nothing special for fractions. When we do whole numbers, we keep the same name. We keep the common name. So when we're adding fractions, having that common denominator is just like having the same name with any other number. And keeping that common denominator is just keeping the same name. When we multiply, let's say I did 3/7 times 2/7. You were taught to just multiply straight across, right? Well, again, that's not a special rule for fractions. When we multiply any numbers, we combine the counts. 3 times 2 is 6. And then we also combine the names. 7 times 7, well, it could be 7 squared, just like the inches squared, but we can multiply it out to just get 49. And just like whole numbers, if I have fractions with different denominators, can I add those two the way they're written? No. Now in a little bit, we're going to look at changing the name on fractions so that we can add them. But for right now, we can't add those. But if we're multiplying 1/4 times 3/5, when we multiply, we don't need the same name. We don't need a common denominator. We're just going to combine the counts. 1 times 3 is 3. And also combine the names. 4 times 5 is 20. Get 3 20s. Other forms of numbers. Decimals, 0.21. What would be the formal way of pronouncing that? Instead of 0.21, we would say 21 hundredths. There we go. And when we write it out that way, it's fairly obvious where's the count and the name. So if we're going to add decimals, so we're going to 0.21 plus 0.3. Is that going to work? What's wrong there? Decimal points aren't lined up. Why do we have to line up the decimal points? It's not just because that third grade teacher said so. Because when we look up here, this is 21 hundredths, but this is 3 tenths. They have different names. You can give them the same name by just putting a 0 there. Now that's 30 hundredths. So when we're lining up the decimal points, all we're really doing is making sure they have the same name. And now we can add. 1 plus 0 is 1, 2 plus 3 is 5. What do we do with the decimal point? We bring it straight down. Why do we bring it straight down? Well, 21 hundredths plus 30 hundredths is going to be 51 hundredths. When we add, we keep the same name. So when we add or subtract decimals, bringing the decimal point straight down is just keeping the same name. Well, when we multiply, let's say I take 0.21 times 0.3, do I have to line up the decimal point? No, I don't. Because when we multiply, we don't need the same name. Well, 21 times 3 is 63. Where does my decimal point go in my answer? You go 1, 2, 3, there's the decimal point. Why? Well, you were taught you had to go to the problem and count 1, 2, 3 decimal places in the problem. Then you got to count backwards 1, 2, 3 decimal places in the answer. But again, why? Third grade teacher said so. Well, this is 21 hundredths. And this is 3 tenths. And 21 times 3 is 63. But when we multiply, we also combine the names. Hundredths times tenths is thousandths. So when we're counting up those decimal places in the problem and making sure we put that many in our answer, all we're doing is combining the names. And this will go right into our algebraic numbers for us. Let's say we have 4x. Again, we look at that and it's just a number with its two parts, a count and a name. 4x is going to behave just like 4 cows or 4 inches or 4 pounds. The difference is we know what an inch or a cow or a pound is. Bless you. We just don't know what x is. But it doesn't matter. 4x plus 9x. We're going to combine the counts. 4 plus 9 is 13. And keep the same name. X and x make x. There stay x. When we're multiplying 4x times 9x, here's why we use the dot instead of the cross for multiplication. We combine the counts. 4 times 9 is 36. But we also combine the names. Just like inches times inches became inches squared, x times x becomes x squared. Or if we have 5x plus 2y, what do we get? Well, trick question. They have different names. We can't add them. It's just 5x plus 2y. But if we were multiplying 5x times 2y, just like 5 feet times 2 pounds, we'd multiply the counts. 5 times 2 is 10. And then also multiply the names. Just like feet times pounds became foot pounds, x times y becomes xy. So you can see there's a lot of connections between the different forms of numbers. All of these different rules that you've been taught for the different types of numbers, are really the same rules. They just look different because the types of numbers look different. Now you might be thinking, okay, that's kind of interesting, but how does it tie into the stuff we do every day? Well, what ties it together is a concept of place value. Now I'm going to breeze through place value pretty quickly because, well, it's most of you hopefully know it all. Starting at the decimal point and working our way backwards, this last digit is the ones, and then tens and hundreds. And those are our three place values. They repeat over and over again. Ones, tens, hundreds. Ones, tens, hundreds. This first group is just the base group. The second group of three is the thousands. And then it's the millions, and so on. And when you name a digit, you name its place value and its group. So this might be just the tens group, tens digit. This is the 10 millions and the 10,000s, and so on. Now, I'm not going to insult you by showing you how to pronounce a number, but I am going to show you this. Let's say we have 5,286. What we're used to seeing there, 5,286, is not the full number. It's just an abbreviation. The full number would look like this. It is 5 thousands and 2 tens, or 2 hundreds, I should say, and 8 tens and 6 ones. Having it in its full form like this explains not only why we do the operations with numbers the way we do, but when we get up into algebra, it's the same reason why we do algebra the way we do. It also, by the way, explains how we round numbers and stuff like that as well. For example, if I were to ask you to round that to the nearest 100. Well, there's the hundreds digit. And to the nearest, we all know how to round, but what it technically means is that we're looking at a number line that's labeled in hundreds. This might be 5,100, 5,200, 5,300, 5,400, and so on. And it's asking us to find that number, 5,286, which would be somewhere in here. And physically, which one is it nearest to? Well, it's nearest to the 5,300. So that would round to 5,300, to the nearest 100. Now, I realize you're not going to draw out number lines when you round. You've all been taught you look at the next digit, and if it's 5 or above, you round up. If it's 4 or less, you round down. And we're not going to spend any more time on that. But let's look at, and just we're going to do one example of each of these and get through them kind of quickly. What if we had 526 plus 231? Now I am going to write these out in expanded form. So this is 500s plus 2 tens and 6 ones. This is 200s plus 3 tens and 1 1. Yeah. Yeah, I'm never going to make you write them out full form. I'm just doing this now so you can see. Yeah, I'm not going to make you like expand out the numbers or anything like that. Listen, I never grade the homework, so as long as you look at it and you are comfortable with knowing what you're doing. I mean, to be honest, especially this first couple of weeks, if you start the homework, do the first couple of problems, and you're thinking this is really easy, feel free to skip ahead. And I'm not about having you sitting there doing busy work, doing problems you already know how to do. And math can be boring enough without putting you through that. As long as you're comfortable that you're ready to take a test, I'm okay with it. So when we look at this, we just said a few minutes ago that when we add numbers, we can only add things that have the same name. Well, you can see here that each digit has a count and a name. 5 hundreds, 2 tens. We've always been taught when you add or subtract, you have to line up the columns. Well, the reason is when we add or subtract, we can only combine things right down to the digit that have the same name. We can only combine 2 tens with 3 tens and the 500s with the 200s. Once we have them lined up, then we just add or subtract right down the columns. 5 and 2 make 7, 2 and 3 make 5 tens, and 6 and 1 make 7 ones, 757. Now, some of you might be thinking right now, he did that backwards. He started on the right and went to the, or started on the left and went to the right. How have you always been told we needed to do subtract or addition? Right to left. Why? Well, in case we have to carry. Good. We might have something like this. 672 plus 198. We've been taught to start on the right and work our way backwards to the left because we run into this. 2 plus 8 is 10. Well, we can't have 2 digits there, so we're going to keep the 0 and carry the 1. 1 and 7 is 8, plus 9 is 17, so we're going to keep the 7 and carry the 1. 1 and 6 is 7, plus 1 is 8, so 807. Believe it or not, that process of carrying is a relatively new process. It's only about 150 years old. Before then, addition looked a little differently. Now, you don't have to write this down. I'm never going to make you do it differently. I'm just showing it to you because everybody's been taught there's only one right way to do problems in math. It's not. I could actually show you 3 or 4 different ways to add numbers that'll work out every time. It's just, this is the most common way of doing it. But once upon a time, when you were to add things like this, it would have looked like this. 6 plus 1 makes 7. 7 and 9 makes 16, drop the 1. 2 and 8 makes 10, so 0, drop the 1. 7 and 1 is 8, 6 and 1 is 7, and 0. You can see we get to the same answer. It's a little bit longer, but the main point is there isn't just one right way to do things. Especially when we get into the dosage calculations, there's going to be 4 or 5 different ways you can go about getting to the answer that'll work. We're going to try to narrow it down to a couple of processes that work best for you. Now, also, I'm a realist. I realize that after we get through this first test and you've taken that section that you can't use the calculator on, not too many of you are going to do 3-digit addition without using a calculator. It's there, you're probably going to use it. But at the very least, I would hope that when you look at a problem like this, you're going to say, okay, this is close to 700. This is close to 200. I'm expecting an answer to be around 900. Because if you're anything like me, of course, you're probably not quite as bad. I have these fat fingers. When I go to punch buttons on my calculator, it's really easy for me to hit a second button or think I pressed the button and it didn't register or whatever. And it wouldn't be terribly uncommon for me to try to do something like this, punch it in and get an answer like 6,770. Well, I hit an extra key somewhere. And if I'm not paying attention, I write that answer down and go on with life and I don't catch it. Well, especially in the medical field, that's a major problem. So make sure before you're punching things in that calculator that you have an idea in your head of what it should come out to be. Subtraction then, of course, is going to follow the exact same rules. I'm not going to bother writing this out in long form, because you guys get the point of, you can only add hundreds to hundreds and tens to tens, and the same with subtraction. So if we have our columns lined up, we can just subtract right down the columns. 8 minus 2 is 6, 7 minus 5 is 2, 4 minus 1 is 3. Now again, some of you are probably thinking, he went backwards again. And I did. We've always been taught to go the other direction, from right back to left, in case we need to. On subtraction, it would be borrowing, right? No problem. Let's say we have 974 minus 389. We've been taught to go from the right to the left because we run into 4 minus 9 can't be done, so we're going to borrow from the 7. That's now a 6, and this is a 14. 14 minus 9 is 5. 6 minus 8 can't be done, so we'll borrow from the 9. That's an 8, and this is now a 16. 16 minus 8, 8. 8 minus 3 is 5. Well, just like with addition, there are other ways to do subtraction. Again, you don't need to write this down. I'm just going to show you for my own amusement mostly, but just to prove that there are other ways to subtract. One other method, in fact, this is still done in some foreign countries, would be 9 minus 3 is 6. 7 minus 8 can't be done, so we borrow from the 6. That's a 5. This is 17. 17 minus 8 is 9. 4 minus 9 can't be done. Borrow from the 9. It's an 8. This is 14. 14 minus 9 is 5. So 585. Get the same answer. Again, I don't expect you to change how you subtract, but it's always nice to know that there isn't just one right way to do things. Multiplication. Let's say we have like 32 times 23. I am going to write this out in its full form. 3 tens and 2 ones times 2 tens and 3 ones. We said that when you multiply, you don't need the same name, which means not only can this 2 ones be combined with these 2 ones, but it can also be combined with the tens. In fact, every digit in one number can be combined with every digit in the other number. And long multiplication is nothing more than an organized way of making sure that happens, that every digit in one number gets multiplied or combined with every digit in the other number. So we usually start with this last digit in the bottom number, the 3 ones, and we'll combine it with the 2 ones. So we combine the counts. 3 times 2 is 6. We also combine the names. 1s times 1s is 1s. Now we're going to keep the 3 ones. We're going to combine it with the next digit in the top number. 3 1s times 2 10s. Well, 3 times 3 is 9. We've combined the counts. 1s times 10s is 10s. Now we've taken that 3 ones and we've combined it with every digit in the top number. So now we move over to the next digit. I've always been taught that when we move over, what do we have to do down here? Add a 0 here. And the reason for that will become obvious here in the next second or two. So we've got 2 tens. We're going to combine it with 2 ones. We combine the counts. 2 times 2 is 4. But we also combine the names. 1s times, or 10s times 1s is 10s. We had to have that 0 there so that our 10s stayed lined up. And now we have the 2 tens times 3 tens. 2 times 3 is 6. 10s times 10s is hundreds. So when we do multiplication, because we don't need the same name, every digit in one number has to combine with every digit in the other number. And all this stuff we do down here with putting in the zeros and stuff is just to make sure our place values stay lined up down there. And now we would just combine. We got 6 ones, 9 and 4 make 13 tens, so if we carry the 1, 736. Now again, just like with the addition and subtraction, I know that the calculator is going to become involved when you're allowed to. So I would look at this and say, okay, that's about 30. This is about 20. 30 times 20 is 600. Now 736 is a little ways away from that, but at least we know we're in the ballpark. Now we didn't get something like 3,000 whatever. Let's take a look at long division and then we'll take a little break. Long division is probably the operation, well, division in general is the operation that has been altered and shortened the most, to the point where most people don't even really recognize the division anymore. What you were taught from long division is an extremely abbreviated process. So I'm going to show you the true long division process. Now you don't have to write it down because I'm not going to ask you to change how you divide. But if you see the full process, it actually explains all those steps we were taught to do when we do long division. So to start out, let's kind of tie some things together here. Looking back at multiplication, 5 times 3. Now we all know it's 15. But if you go back to kindergarten or first grade, before you started memorizing the multiplication tables, before you had memorized that 5 times 3 was 15, how did you figure that out? Yeah, 5 plus 5 plus 5, right? Did repeated addition. It's 15. Multiplication is actually defined to be repeated addition. Well, we said that division was just multiplication done in reverse. So if division follows the same rules as multiplication, it makes sense that division is repeated subtraction. 24 minus 8 would be 16, that's once. 16 minus 8 would be 8, that's twice. Subtracting 8 again is 0, that is 3 times. 24 divided by 8 is 3, because I can subtract 8 from 24 3 times. In fact, that's actually how we get our remainders and all that as well. Let's say we have 27 divided by 6. We start out with 27, we subtract 6, that's once, get 21. Subtract 6 again to get 15, that's twice. Subtract 6 again to get 9, that's 3 times. Subtract 6 again, that's 3, that's 4 times. So in 27 divided by 6, it goes in there 4 times with 3 left over, so a remainder of 3. Now with that in mind, let's take a peek at long division. So let's take 31,879 and divide by 23. Now we just said that division was repeated subtraction. I am not about to start subtracting 23 from 31,000. We don't have that kind of time. But if I could subtract like a whole bunch of 23s all at once, it would speed up the process. And that's what long division is. And the way we figure out how big of a bunch is we look at the place values of the number we're dividing. The first digit here is in what place value? The 10,000s, right? So if I take 10,000 times 23, I get 230,000. Can I subtract 230,000 from that? No, it's too big. The next place value would be the thousands. Times 23 would be 23,000. Can I subtract that? Yes, I can. Can I do it more than once? No, I can only subtract it once. So if I subtract 23,000, I am left with 8,879. I just subtracted 23 1,000 times. My next place value would be the hundreds. 100 times 23 is 2,300. Can I subtract that from what's left there? Yes, I can. And so, in fact, I can subtract it 3 times. 2,300 times 3 is 6,900. Leaving me with 1,000. Oops, that's wrong. 1,979. Well, I didn't subtract 2,300 3 times. What I really did was I subtracted 123s 3 times. 100 times 3 is 300. I just subtracted 300 more 23s. The next place value is 10 times 23 is 230. Can I subtract that from what's left? Yes, I can. Let's see. 8 would be too many. Let's do 7. Let's try 7. 7 times 0, 7 times 3 is 21. Carry the 2, 14, 16. Could I have done it 8 times? I don't think so. Well, let's subtract. Let's see what we get. Yeah, we could have gone another one. Let's go 8. So 8 times 0, 4, carry the 2, 1840. Yes, we couldn't subtract it 8 times. So subtracting there, we've got 9, 3, 1, 139. Well, again, we didn't really subtract 238 times. We subtracted 10 sets of 23 8 times. 10 times 8 is 80. We just subtracted 80 more 23s. So, of course, the last place value is 1. So 1 times 23 is just 23. Let's do 6 times. That'd be 138 with 1 left over. So we just subtracted 23 6 more times, and there's a remainder of 1. So that's 1,386 with a remainder of 1. That's a long process. There's a reason why they wanted to shorten it up. It takes a lot of space and time and paper. But if we look, and you're probably looking at it thinking, that's nothing like what I was taught. But it is. Let's look at the similarities here. Most of us were taught to do this. You start out, you take the 23, Can 23 go into 3? No, it can't. So we leave it blank there. That's the same as checking to see if we can subtract the 10,023s. We can't, so we moved on to the next spot. Can 23 go into 31? Yes, it can. It goes once. We put the 1 above that because that's the last digit we used. Then 1 times 23 is 23. We subtract to get 8. Then we start bringing down the other digits. Well, if we look at what happened here, it's exactly the same as what happened over here, only we left off the zeros. So it's the same process. Now, I also understand that when you do long division after the first test and I allow you to start using it, you're going to use the calculator. To be honest, long division is the one operation that I use the calculator for whenever I can as well. I don't expect you to change how you divide. I wanted to show you this because for some people, seeing where it came from actually helps make more sense as to why we do long division the way we do. With that, let's take our break. Let's try to come back at about 9:35.